first video of Unit 4 is going to focus on describing the electron orbitals and the rules for filling them with electrons. So let's remember the atomic theories that we learned earlier. Dalton came up with a four-part theory about atoms. Some parts were right, some were not. Then Thomson came up with the plum pudding model saying that electrons were scattered throughout a positively charged material. Rutherford conducted the gold foil experiment and discovers the nucleus and that most of the atom is actually empty space. Now, Bohr is the first one to come along and say where the electrons might be outside of the nucleus, and he says that they orbit the nucleus much like planets orbit around the sun. Then Schrödinger comes along with the quantum mechanical model, and there's a positive nucleus, and then the electrons are in a cloud, and in his model they show the locations of highest probability that electrons can be found like 90% of the time. So we're going to focus on the quantum mechanical model now. And the first thing you need to understand is what are energy levels. So these rings around the nucleus are considered general locations where electrons can be found a high probability of the time. So here would be the first energy level, this would be the second energy level, and this would be the third energy level, and so forth. Okay? If you have an electron on the first energy level, it is closest to the nucleus, which means it has the lowest or least amount of energy. The further electrons get from the nucleus to higher energy levels, the more energy that they have. So you can think of it like a ladder. If you're at the bottom of the ladder, you're at the lowest point of the ladder, you have the lowest amount of energy. And then as you climb the ladder and get higher and higher, then you have a higher amount of energy. Okay? Also, you become further away from the nucleus. Energy levels are also known as principal quantum numbers, which are denoted with a lowercase n. So on the periodic table we have rows. This is row number 1. The elements on row number 1 have one energy level, or a principal quantum number n equals 1. So hydrogen and helium have only one energy level. Row number 2, lithium, beryllium, boron, all the way to neon, they're on row 2. These elements have 2 energy levels. Then any element on row 3, these elements have 3 energy levels. Row 4 has 4 energy levels. Row 5 has 5 energy levels. Row 6 has 6 energy levels. And row 7, which is the last row, has 7 energy levels. So, to answer some of our questions here, if the element is in period 5, period and row are the same thing. Period 5 is 1, 2, 3, 4, 5. This is period number 5. And so if an element is in period 5, it's going to have 5 energy levels. How many energy levels does iodine have? Well, iodine is located here, and conveniently that is row 5 or period 5, so it has 5 energy levels. Finally, what is the most energy levels the atom can have? And remember that we could get all the way down to 7 rows on the periodic table, so 7 energy levels is the highest an atom could have. Here is an example of an atom where I've denoted each energy level with n equals and the number that the energy level is. So n equals 1 is closest to the nucleus, least amount of energy on these electrons. And then this is n equal 2, n equal 3, 4, 5, 6, and 7. So the farther out the electron is from the nucleus, the more energy that electron has. Next is sublevels. Within each energy level, there are sublevels, 4 to be exact. You should know that there is S, P, D, and F are the names of the sublevels. The principal quantum number n is equal to the number of sublevels. So if you have an n equal 1, then there's only one sublevel, and it's going to be the first one, S. So we can have a 1 followed by S. N equals 2 means we're going to have a 2 in front of S and P, 2 sublevels. We go in order, S, P, D, F. So we have a 2s and a 2p. If n is equal to 3, then we can have 3s, 3p, and 3d. And if n is equal to 4, we can have 4s, 4p, 4d, 4f. How many electrons can be in each level? So 2n squared is the equation to calculate this. So in the first energy level, where n is equal to 1, I'm going to take 2 times 1 squared, and that equals 2 electrons maximum in that energy level. In the second energy level, where n equals 2, 2 times 2 squared is equal to 8 electrons maximum. If n is equal to 3, then 2 times 3 squared equals 18 maximum electrons on that energy level. So how many electrons can we fit in the fourth energy level? We want to say 2 times 4 squared, and that's going to equal, 4 squared is 16, 2 times 16 is 32 electrons that can fit on the fourth energy level. So now let's talk about each sublevel individually. The S sublevel is spherical in shape. It's only one orbital, and for us, orbitals are denoted by blanks. And one orbital can hold one pair of electrons or 2 electrons. Think back to our hogs, only 2 hogs in a room maximum. This is always the first orbital filled for any energy level. The s orbital makes up families 1a, 2a, and helium on the periodic table, so that's denoted in orange in this periodic table on the left, or over here it's also highlighted and boxed in orange. The p sublevel has dumbbell-shaped orbitals. There are 3 orbitals total, x, y, and z, here, here, and here. Notice that it makes the figure 8 is another way to think of it. Electrons go in the p orbital after the s orbital is filled. The p orbital makes up families 3a through 8a on the periodic table. So the p orbitals are going to be this blue block on the periodic table. And so here you can see where we have our nucleus. Here's a 2s orbital, and then here's our 3 2p orbitals, and they're in a vertical, horizontal, and a diagonal. Okay, so this is like the 2p on the y-axis, the 2p on the x-axis, and the 2p on the z-axis. The d sublevel is cloverleaf shaped. There are 5 orbitals, d1, d2, d3, d4, d5. So basically that means that your d clover-shaped sublevel can sit in 5 different positions in the XYZ plane. Electrons only go in the d orbital after the s and p orbitals are filled. The d orbital is also made up of the transition metals. So this gold section of the periodic table is where all the d orbitals lie. The f sublevel, these orbitals have complex shapes. There are 7 orbitals, and that means that there are 7 different ways the f orbital can be oriented in the 3D plane. F orbital is made up of the rare earth elements, also called the inner transition metals. So this green block down here is known as the F block. Electrons are located in orbitals within each sublevel. One orbital can hold 2 electrons. Now remember, on paper we're going to represent orbitals with blanks or boxes, and then electrons are represented with arrows. So if you have an s sublevel, then you're going to have one orbital that can hold 2 electrons maximum. A p sublevel can have 3 orbitals and a maximum of 6 electrons. D will hold 5 orbitals, max of 10 electrons, and F will have 7 orbitals at a max of 14 electrons. Use the periodic table to answer the questions below. Find aluminum on the periodic table and what period is it in. So here is aluminum here. It is in period 1, 2, 3, which means that it has 3 energy levels, and the block that it's located in is the P block. So what block is it in? It's in the P block. This represents the last orbital to contain electrons. So it's on row 3, it's in the P block, P, and then which P block is it in? 1, 2, 3, 4, 5, or 6. It's in the first P block, first column in the P block. So this is going to be 3p1, would be the last orbital to contain electrons for aluminum. So what sublevel is the last one to contain electrons in magnesium? Well, first of all, here's magnesium, right here. It is on row number 3, row 1, row 2, row 3. All right, so it's in row 3. It's in the S block, so I'm going to say 3S, and it's in the second column of the S block, so it's 3S2 is going to be the last sublevel to contain electrons for magnesium. So let's write the full electron configuration of magnesium. I'm going to go across the first row, so it's going to be 1s2. Then I'm going to go across the second row, 2s2, 2p6. And then I'm going to go across the third row and I'm going to stop at magnesium, so it's going to be 3s2. And there's the full electron configuration of magnesium. What is the last orbital to contain germanium electrons? So there's germanium. It is on row 1, 2, 3, 4. So because it's on row 4 and it's in the p block and it's 4p 1, 2, it's in the second column. This is going to be 4p2. That's the last thing on the germanium's electron configuration. So now let's write the full electron configuration. So we have our first row, it's going to go 1s2. Second row, we're going to say 2s2, 2p6. Third row is going to say 3s2, 3p6. And now we're on the fourth row. This is tricky. 4s2, and then right here we get a change in row number. This is 3, 4, 5, 6. When you get in the D block, it's the row number minus 1. So it's going to be 4s2, 3d10, and then 4p2. And that's the full electron configuration for germanium. Again, notice that the very last part matches up here. This may very well be the most important slide of the entire presentation, and it would be how to write an electron configuration for any element on the periodic table, just about. So we're going to read the periodic table from left to right and then top to bottom. So from left to right, row number 1, it goes 1s1, 1s2. So that would be hydrogen would be 1s1, helium would be 1s2. So you would write 1s2 followed by 2s2 and then 2p6. We jump across. So 2s2, 2p6. Next is 3s2, 3p6. 3s2, 3p6. Now, we're on row 4 and things get a little bit different on row number 4. So notice that here is the D block and it becomes the row number minus 1 is the energy level of the D block. So it's going to be 3, 4, 5, 6, which it states here 3D, 4D, 5D, 6D. Okay, so it's going to go 4s2, 3d10, 4p6. 4s2, 3d10, 4p6. Followed by 5s2, 4d10, 5p6. 5s2, 4d10, 5p6. Now, it gets even stranger. We're going to have 6s2, and then we actually jump down to the F sublevel, which is the row number minus 2. So this is going to be 4f and 5f. So it's going to go 6s2, 4f14. I'll go ahead and denote those. 6s2, 4f14. We come back after the end of 4f, we come back to 5d10. And you can notice this on the periodic table with the atomic numbers, that it goes 6s2 and then the next atomic number is down here. And then when you get to the end of this row, the next atomic number is at this point, and then we go forward. So it's not like you have to remember that. You can use atomic numbers to figure it out. So after 4f14, it goes 5d10, 5d10, followed by 6p6. Do you think you can figure out what it would be from the beginning of row 7 all the way to the end of here? When you're writing electron configurations, you're going to go in this order, but you're always going to stop at whatever element it is that you want. So if our final element is this element right here, then it's going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p1, because I stop one block into the p block. So now I would like for you to practice writing the full electron configurations of the following elements. These are in your note packet. Those of you that are online, these are posted on Canvas, and then we will check your answers. You'll submit these and then we'll check them.